the atom, the structure of water, what is pH. Those are things you're supposed to know already. I'm not even going to talk about it. It won't be on a quiz or a midterm. I mean, it would be like if I were teaching a literature class and I started out by teaching the alphabet. You know, you're supposed to already know it. So we are going to start, again, on my book, it's in page, I don't know what page, page 39. Yours might be a little bit different, but basically organic molecules or organic compounds.
34.
34, thank you. Well, 34 then in the book you have. Organic molecules. So we're skipping completely the stuff before that. I mean, we just don't care. So, now, what exactly is an organic molecule? What does that mean?
Anything that has carbon?
Anything with carbon. Well, carbon containing. The reason that's an issue is because all living things have carbon. So organic molecules contain carbon. Unfortunately, it does not always work the other way around. Most molecules with carbon are organic, but not all. Does anybody know, we haven't done it of course, but does anybody know an example of a carbon-containing molecule that is not organic?
Carbon dioxide. Carbon dioxide.
Yes, carbon dioxide. CO2, a totally common molecule, we produce it. Got carbon, but it is inorganic.
Why?
I can give you the reason, but I don't really agree with it. But nobody cares if I agree or not. The reason is that apparently to be organic, not only do you have to have carbon, you also need hydrogen. And of course, CO2 doesn't have it. But every other organic molecule has hydrogen along with the carbon. So CO2 is the main exception. There is one more. Carbon monoxide. Carbon monoxide. So the same thing, it's got carbon but no hydrogen. So all organic molecules have carbon. Most molecules with carbon are organic, but you have to now seen there are a couple of exceptions. Okay, so the main organic molecules or biological molecules include carbohydrates, lipids, oops. Lipids, proteins, and nucleic acids. Those are the biological molecules. The carbohydrates, of course, you know, are sugars. Proteins you're familiar with, nucleic acids you're familiar with, you know, DNA, RNA. The one category here you might not really know are the lipids. And the lipids are fats and oils. Fats and oils. In the case of bacteria, not so much fat in a bacteria, but they're significant components of cell membranes. But yeah, in humans or most animals, fats and oils. And lucky you guys, we'll be talking about each one of these. Let's start off with carbohydrates. And specifically, we will start with monosaccharides. Monosaccharides. The prefix mono means one, and the word saccharide is a structural sugar unit. A structural sugar unit. The monosaccharide is literally a sugar with one structural unit. And I realize that's probably not very clear. There are some times when, frankly, I'll just kind of ask you to bear with me. And a lot of times it's easier just to go through and do it and let you kind of figure it out as we go. And this would be one of those times. I'd rather just do it and let you see what it looks like. But that saccharide thing, this is before your time, but the original artificial sweetener was saccharin. And this is, I don't know, 40 years ago, it was saccharin. And that's what everybody had, for their Diet Coke and that kind of thing. It was always saccharin. And then some guy up in Canada was working with white rats and completely overdosing his white rats with saccharin, giving them a lot of the stuff. And they developed cancer. So saccharin was taken off the market because it was believed to be carcinogenic. The rest of us were not very impressed. I still remember the jokes that were coming out about this, saying that yes, if you are a Canadian white rat and you drink 100 cases of Coke a day, then you will get cancer. But I mean, that's about how much stuff they were getting. So most of us weren't very impressed, and but still, it got taken off the market. Now, having said that, I must admit to you, studying cancer is not easy because most things that cause cancer take about 20 years. Like all of you, I'm sure know that studying out the sun, a lot of times 20 years later, people start getting skin cancer. And people who smoke, everybody knows smoking causes cancer. But a lot of times people can go 20, 30, or forever and not get it. So it's always been hard to study cancer. So the only way to really do it, if you don't want to wait 20 or 30 years to start getting results, the only way to do it is to overdose your victim, to overdose your subject. Well, sorry. So if you do that, then yeah, you'll get faster results, but that raises an obvious question. Is it really causing cancer, or is it the overdose that's causing the cancer? And I was only joking a little about the 100 cases of Coke. Obviously, nobody in his right mind we couldn't drink so much. But even if you drank a case a day, that's still an overdose. And maybe that's causing the cancer. So there's always been a built-in flaw in studying cancer. And even though we were kind of laughing at this guy, but he was really doing all that he really could do. Anyhow, back to this. So monosaccharides, we'll talk about the obvious one, glucose. I say obvious because, of course, you all know glucose. Now you can see, it's kind of hard to read, kind of hard to look at. Part of it's my handwriting, but you will learn to love my handwriting. But for right now, you don't. But even beyond the handwriting, it's just a very busy molecule. There's a lot of stuff there to look at. So instead, there's an easier, cleaner way to look at it. Same molecule. Now this is easier to look at, it's cleaner and all the rest of it. The obvious question is, what exactly did I do? What's different about it? There are two assumptions that I'm making here, two assumptions. One assumption is each corner of the ring we assume is a carbon atom, unless we're told otherwise. So here's a carbon, 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 carbon. These are all corners of the ring. Yeah, sorry. These are all corners of the ring. This is a corner of the ring, but here we're being told otherwise. We're being told oxygen. We're being told oxygen. So carbon, 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 carbon. You can compare over here. You can see, yep, those are all carbons. Notice up here, I wrote it in. Keep in mind the wording of that assumption. The wording is each corner of the ring. This is not in the ring. It's outside the ring. So if it's outside the ring, write in everything. Second assumption. This one's actually a little more tricky. It's based on the fact that carbon always has 4 bonds. Carbon makes 4 bonds. That's fact. So the assumption is that wherever carbon seems to not have 4 bonds, then the missing bond is there, and it's always to hydrogen. So that's more tricky. Here's how it works. Here's the corner of the ring, that's carbon. Here's a bond. Here's a bond. There's a bond. So 3 bonds. We seem to be missing a bond. There should be 4. So the missing bond is there, and it's always to hydrogen. If you compare over here, you'll see, yeah, it's there. Let's do that one more time. Let's take this carbon. So again, corner of the ring. That's a carbon. there's a bond, there's a bond, there's a bond. So once again, 3 bonds. We seem to be missing a bond. And it's the hydrogen. It only works if the carbon is bonding hydrogen. If there's something else bonded, nitrogen, sulfur, whatever, if there's something else bonded, you have to put it in. You can't leave it out. So it only works for hydrogen. And again, if you compare over here, you can see those hydrogen links. So that's why it looks cleaner, the one on the right, because I didn't put the carbons in, and I didn't put in those 4th bonds. Actually 6. Actually, you kind of led me somewhere I wanted to go, so thank you. There's a numbering system we can use, which kind of makes things easier. It's not required, but it's easier. Pretend the oxygen is 0. It is oxygen, but pretend it's 0. And then go clockwise. Carbon number 1, 2, 3, 4, 5, and up here 6. And it's the same for both. You still look unsure.
How do we know that always
Because it's glucose.
oh, this is always like that's
Glucose,
that's the
yeah.
formula.
Yeah,
It will never change.
not for glucose.
That is
It can definitely change, but then it won't be glucose.
great.
Then you have something else. Yeah. Yeah, yeah, so glucose has 6 carbons, period. Like I say, if it didn't, then it's not glucose. Another thing on this molecule, for sugars in general, these OH groups, they're extremely common. You're going to see those all quartered. They're called hydroxyl groups. Hydroxyl groups. They're extremely common. And since hopefully you've had chemistry already, you should be fairly familiar with that. It's so common. Notice this negative sign in front. The negative sign is not a negative sign. It's an open bond. It's an open bond. By an open bond, what that means is it wants to bond to something else. Like, for example, glucose. All of these are hydroxyl groups. By the way, the CH2OH, remember carbon always has 4 bonds? There's your 4 bonds. 1 bond, 1 bond, 1 bond, 1 bond. So hydroxyl groups really are actually negatives. But that goes there. That's the negative charge. This, despite that it looks like a negative, it's not. It's an open bond. It wants to bond to something else. So again, hydroxyl groups, you're gonna see those all over the place. Any questions about glucose? I'm just getting rolling here. That means there's more coming. Okay. I'm going to get rid of this. We don't need it. It was really just for demonstration. We're going to use this. The monosaccharide is just simply a single structure. So monosaccharide. Let's do a similar molecule. Galactose. Pardon me? Oh, H over OH, it doesn't matter. No, yeah, thank you. That's a point I need to make. Whether I do OH or HO is irrelevant. See, the bond is always the oxygen. Oxygen can make two bonds. Hydrogen only makes one bond. So hydrogen's always on the outside. It's never in the middle. So the bond is the oxygen, and then you can put hydrogen there, you can put hydrogen there, you can put hydrogen there, it doesn't matter. So whatever works. But the bond is always the oxygen, and then put the hydrogen wherever. Thank you for mentioning that, because I should have said that. So this is galactose, looks very similar to glucose. And the only difference is this hydroxyl group over here. For glucose, it points downwards. For galactose, it points upwards. And it looks like not much of a difference, but it's enough. That is the difference.
So what's the point?
What?
What's the point of it?
It's a different molecule.
But then what does that end? That's glucose.
No, galactose is just simply a different monosaccharide. There's a million of these monosaccharides. And many of them are no different than that. They're just simply a different sugar. So different sugars have different bonding properties. So we're going to, it's coming.
So the difference between the galactose and the glucose.
I'm sorry?
The difference between the galactose and the glucose is that one hydroxyl
Yes.
group is going upward.
Yes, that is the difference. And you move the hydroxyl, yeah. So another way of explaining this or commenting on it, the difference between glucose and galactose is the number 4 hydroxyl. So that's the way you need to know the numbering. So again, use oxygen as your 0 and go clockwise. Carbon number 1, number 2, number 3, 4, 5, and 6. So the difference is the number 4 carbon or the number 4 hydroxyl. For glucose, the number 4 hydroxyl points downwards. For galactose, it points upwards. That is the difference. Now, I don't know the names yet, but she was asking, well, what's the point of it? What difference does it make? It gives you a different molecule, and we're going to see in a minute why that makes a difference. So for right now, kind of bear with me. But different molecules in different locations, or groups in different locations, give you different bonding different bonding gives you different properties. Okay, one more of these monosaccharide. Yeah.
Can the bond only be going up or down?
For, no, actually for this, it's up or down. It won't go outwards. So one more of these monosaccharides. This one's fructose. It's the sugar found in fruit, apples and oranges and that kind of stuff. Despite how it looks, it also has 6 carbons. The numbering here, you still start with oxygen as your 0, but now this is your number 1 carbon out here. And then number 2, 3, 4, 5, and 6. So that's fruit sugar, fructose. Pardon me? No. It's the fewest number that I've given you, but there's many, 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 many. Okay, so these are all monosaccharides. As I was just commenting, there's many more of these examples. We can't spend the rest of our lives doing it. So let's move on to the next category. These are monosaccharides, sugars with 1 structural unit. Let's go to disaccharides. Obviously, sugars with 2 structural units. And I want to start off with 2 glucoses. So I'm going to change this. I turn that into a glucose. I've got a glucose here. So two glucoses. Remember, I want a disaccharide. I want a molecule with 2 structural units. That's what the di means. The problem is, I don't have a disaccharide. What I have are 2 monosaccharides. That's not a disaccharide. So what I have to do is to combine the 2 monosaccharides into 1 disaccharide. Notice here and here, 2 hydroxyl groups. 2 hydroxyl groups. Here and here. What you want to do is to take one of them. It doesn't matter which. It doesn't matter. So I'll take this one, just because I've got to take one of them. On the other side, take a hydrogen. So taking out hydroxyl, taking out hydrogen, I won't insult you by asking, what we're taking out is water. We're removing water. We're taking out water. Hydroxyl here, hydrogen here. We're taking out water, leaving behind a single oxygen. Leaving behind a single oxygen because we took out the hydroxyl from one side, hydrogen from the other. And that now will connect to the other side. Pardon me? Oh, yeah. So that's what we're starting with, 2 glucoses. Hydroxyl here, hydroxyl here. Take one of them, I'll take out this hydroxyl. On the other side, take out the hydrogen. So take out a hydroxyl, take out a hydrogen, that's water. We're taking out water. Leaving behind the oxygen. And that will connect to the other side. This is now your disaccharide. It's called a condensation reaction. Or dehydration.
Everything else is still,
Pardon me?
everything else is still in the molecule, so.
And nothing else has changed. It's just that those 2 hydroxyls. Now the condensation is because we're condensing 2 molecules into 1. That's your condensation. Yeah, you're starting with 2 monosaccharides. Now you have 1 disaccharide. That's condensation. You're condensing 2 molecules into 1. Or dehydration. You're dehydrating. You took out water. You took out water. And in case you halfway cared, which probably you don't, you might kind of wonder, where does the water go? Well, actually, bacteria and almost all organisms, people and birds and everything, we're all about 70% water. We're all about 70%. So in this case, that single molecule of water that's being removed, it's like a drop of water into the ocean. It just joins the other 70% of the water, and we don't really know where it goes, so we lose track of it. But again, the organism, whether bacteria or human or whatever, 70% water. So it just joins the rest of it. Sorry. Okay, so anyhow, condensation or dehydration, both are okay. We now have a disaccharide. What that means is we do not have 2 monosaccharides. We cannot use glucose anymore. Glucose is a monosaccharide. What we now have is maltose. Maltose is a disaccharide made up of two glucose molecules. Yeah, maltose is a disaccharide made up of two glucose molecules. And maltose, it's a sugar found in malt. So beer, milkshakes, malted milk balls. That's where you find maltose.
So they remove water to create those.
So you're removing water to create that. It's a very, very, very common reaction. You guys see it all quarter. And fortunately, it's easy. You just take out water. Take out hydroxyl from one side, hydrogen from the other. That's your hydroxyl. And then you link up whatever's left. It's extremely common.
You do that to like use glucose and fructose?
We're going to,
Okay.
but probably not tonight. He was asking about can you do with glucose and fructose. But I actually want to stick here a little bit longer using, instead of glucose, I want to use galactose. So let's go back kind of to the beginning. So once again, glucose here, galactose over there. And we need to combine them into a disaccharide. So we're going to do the same exact thing. Take out a hydroxyl. Like I say, it doesn't matter which side. It doesn't matter. Take out the hydrogen on the other side. So once again, you're taking out water. Leaving behind the oxygen. Once again, water comes out. Leaving behind oxygen. So it's exactly the same reaction, exactly. I'm sorry. What? So glucose and galactose is also a disaccharide. This one is called lactose. This is lactose. See, once again, we no longer have monosaccharides. So we cannot use glucose and galactose. So the disaccharide, this is lactose. Obviously, milk sugar. So two glucoses give us maltose, but glucose and galactose gives us lactose. So obviously, you're all familiar with that. If nothing else, we're all familiar with people who are lactose intolerant. Lactose intolerance is not an allergy. Some people think it is. It's not an allergy. Allergies are different. Lactose intolerance is not having the enzyme to break down lactose. Now, for example, disaccharide if we were to digest the dairy product. And this is true for any of our digestion. We've been making molecules by taking out water to break down the molecule, put the water back in.